Hello, everyone, and welcome to our talk, Bringing Efficient Spatiotemporal Super Resolution to Mobile. I'm Panos, and I'm a software engineer at Arm. And today I'm representing my colleague Sergio, who did the majority of the work on this, but couldn't be here today with us to talk about it. Apparently, he took his remaining vacation. Good for him. I spent them all. Anyway. In today's talk, we'll cover the following topics, but first we need to address something really important. In reality, Arm accuracy super resolution is FSR2, but optimized for mobile. What is FSR2 and why FSR2 is something that we will be discussing today. We'll give a high-level overview of the reasons that motivated us to do this work and why eventually we went down this path. We will also cover how we were validating our steps during this optimization phase, because quality was something really important for us from the start. Then we'll discuss our optimization journey, and finally we'll go through quality presets, deployment, and some conclusions. So yeah, as we move forward, we see mobile devices becoming more capable and slowly closing the gap to large screen compute. New features are getting adopted more quickly, and the performance is slowly converging as well. The result is ports of desktop and console games arriving to mobile, and general mobile games are becoming more ambitious when it comes to graphical fidelity. The reality, though, is that we're talking about very small devices that are running using a battery, and this will always be an inescapable limiting factor. Furthermore, smartphone devices tend to have really high resolution screens and really high pixel density. So we need to work smarter in order to keep the frame budget and power consumption under control. The cost of many rendering workloads that happen in a frame scale proportionally to resolution, and resolution increases time, power also increase, and as a result, battery consumption. And this is where the super resolution comes into the picture. Render a fraction of your pixels, and then somehow magically reconstruct the rest. Desktop and consoles already have solutions around this area, but on mobile, we feel that there is a gap. So when it comes to reconstruction techniques, there are multiple solutions nowadays that vary on quality and complexity. In the past, we've seen things like interlacing, checkerboard rendering, and spatial upscaling. And in recent years, we have moved to more complex and capable spatiotemporal upscaling, algorithmic one like FSR2, and ML-based like DLSS and XSS. Some of those techniques interact heavily with anti-aliasing. In fact, spatiotemporal upscalers are an evolution of temporal AA. When it comes to spatial upscalers, we have FSR1 and GSR1 that are most popular ones in today's mobile content. And this is because of their simplicity and performance. FSR1, for example, is one or two very quick passes. And upscaling from resolutions that are above or equal to 70% of the target resolution is advisable. And if less, the result starts to becoming a bit blurry and not pleasing. Spatial upscalers typically require an anti-aliased image and tone map as well, and maybe some texture bias to retrieve some of the loss in texture sharpness, and nothing else really. And to put things into perspective, FSR1 on an Immortalis G720 device that upscales to a target resolution of 1080p from a 70% input and runs the two FSR1 passes, which is the upscaling and sharpening. It actually runs around 0.7 milliseconds, which is quite nice. On the other side, we have spatial temporal upscalers. The main idea is to reconstruct the high-resolution signal by integrating spatially and temporally across multiple frames. They are quite more sophisticated than spatial upscalers, and they also provide built-in AA. They can also be used for more aggressive upscaling, so the 70% thing I mentioned later becomes even less with them. In this space, we have engine-specific and engine-agnostic solutions, and the majority of them target desktop and consoles. When it comes to the input of the spatiotemporal upscalers, we need the jittered input images. We also need to adjust the MIB bias as if we are rendering in the target resolution, need motion vectors and depth, and some additional optional input for some upscalers, at least. So now that we have an idea, what would we do if we wanted to build a new upscaler? The spatial upscaling is already covered, but we feel there is a gap on more sophisticated solutions in mobile, at least. Another requirement we have is that we want an engine-agnostic solution with a very minimum barrier of entry. So we want easy integration, in other words. And the API needs to be compatible with existing solutions, again, for easier integration. So now we arrive to FSR2, but before we continue, special thanks to AMD and the people who worked on FSR2 for creating it and, more importantly, releasing it as open source for everyone else. And the question really is, why reinvent the wheel when there is something that is widely adopted, popular, very capable, and open, like FSR2? FSR2 is a fantastic upscaler, but it was developed, as I mentioned, with desktop and consoles in mind, and mobile devices have different considerations. They are different architectures, first, and they also need to be, you need to be extra careful when it comes to bandwidth, because that translates to power consumption. Running FSR2 on a recent Immortalis G720 device with a target resolution of 2400 by 1080, the total duration of the upscaling can vary from 6.5 to 8.7 milliseconds per frame, which is quite a lot. Similar story for bandwidth, which ranges from 256 to 385 megabytes per frame. Again, it's a little bit high. As you mentioned earlier, we were happy with the quality FSR2 gives us, but the performance is not quite there, at least for our devices. And in the following sections, we'll go through the process of optimizing FSR2. But before we dive into the optimizations we did, we'll quickly go through the process we used to validate our steps during this process, because it was really important, and you will see why. Optimizing algorithms and cutting corners, of course, may affect quality negatively. So we need to guarantee that this won't happen. And of course, we cannot rely on our eyes to do so. And for that, we need a better approach. So the main idea is we get a pre-generated set of inputs, which we call dataset. We feed this dataset to the upscaler, produce output, and we compare this output against some ground truth or against other upscalers. What is a dataset? It's all the necessary resources required for an upscaler to function in isolation. A dataset for a specific frame contains the ground truth image, the downscaled images, of course, which can be color, depth, and motion vectors. and a JSON file with some metadata. To gather the datasets, we developed an Unreal 5 plugin that captures and dumps the data into the disk. We also created various scenarios that can stress test the upscalers. And we also used our internal demos as testbeds, steel arms and Mori. And you can see them in the screenshots there. These scenarios are called image quality benchmarks. They are 50 frames each, and they are designed to stress test the upscalers, especially temporal ones. They include things like particles, skin characters, both static and dynamic cameras, translucency, animated lighting conditions, and moving shadows, and a few more scenarios. Our first stop of generating this dataset is the ground truth. And we start by capturing a specific fixed, using a specific fixed timestamp that is used to emulate the frame rate we want to target, 30 or 60. We render at 8K resolution, and then we use a box filter to scale it down to 1080p. So every pixel of this 1080p image is the average of 16 pixels. Then we need to produce what will become the input color and input depth of the upscaler. Using a Halton sequence, we pick a different sample inside an 8x8 tile of the 8K image. One sample for color and one for depth. And these samples become the 540p input images. We have a slightly different process for motion vectors because motion vectors should be unjittered. We expose two textures of motion vectors, 540p and 1080p. For the 540p, we pick the closest sample based on depth and in its 8x8 tile of this original 8K velocity texture. For the 1080p, we pick a sample within a 4x4 tile. The 540p is used as an input to the upscaler, as someone would expect. And the 1080p, because of its higher quality, is used for debugging, really, things like reprojection, for example. And motion vectors are stored in UV space. The final piece of the puzzle is the JSON file that contains information common to all frames. Things like target frame rate, the tone map operator used, and a few other additional values. And we have per frame info like frame index, field of view in both axes, near and far camera planes, view projection metrics, exposure, and the jitter offsets. The datasets are fed into a standalone application that implements a few popular upscalers. We have added support for several of them, including DLSS, and of course, FSR2 and ASR. And the result of the upscaling is used in the image quality workflow for comparison studies. The image quality workflow generates metrics for each frame and globally for the whole dataset. The per frame metrics are used to create nice plots useful for really visualizing the various metrics across frames. We'll have some examples later in the following slide, really. The metrics used are pretty standard, and I won't go into details. You can view them in the screen. The final thing that image quality workflow produces is diff images, and they are an additional way to visualize the quality differences. So once we had the entire workflow up and running, it was time to start generating and comparing the various upscalers. As expected, the FSR2 outperformed the spatial upscalers, and it proved to be quite close to the ground truth. So we were in the right track to start iterating with FSR2 as our baseline. So now let's dive to the actual optimizations. This is a complex diagram of FSR2, lots of input, lots of passes. But let's start from the top. We start with the compute luminance pyramid, which is a reduction algorithm to calculate luminance values and write them into MIPS of a texture pyramid. It's used mostly for stability. Reconstruct previous depth, does dilation of depth and motion vectors, also reconstructs the previous depth frame dilated depth by reprojecting the current frame's dilated values. Depth clip builds a final version of a reactive mask using the occlusion data and the user's provided input masks, and will be used to guide the temporal accumulation. LogPass builds a mask with pixels that were identified as thin details and thus candidates for temporal instability. Accumulate pass, history projection, apply heuristics for visibility, spatial upscaling. If sharpening is not enabled, this will be the final output of FSR. And finally, ARCAS, it's optional, that one. It will read the upscaled image from the accumulate pass and apply sharpening and write it to the user's provided output. For the optimization work, we used internal and public tools. When it comes to the public ones, we have the Mali-offline compiler. This will give us a rough idea about the shaders, things like if we have register spilling, if and how much 16-bit instructions the shader is using. And it will also give us an instruction breakdown per hardware unit. The next tool is Streamline. You can see a screenshot at the bottom. On Streamline, we focused on the timeline view, which gives the duration of the passes. We also looked at bandwidth and a few other counters. For the rest of the talk, we will assume an Immortalis D720 device with a display resolution of 2400 by 1080. But before we start, we actually need to set a target. So we took some frame of some demo we had, and we divided it into 3 parts. The work that happens before temporal AA. This will be rendered at the internal resolution. Temporal AA itself. And the final thing is the work that happens after temporal AA, which is post-processing and UI rendering, typically. Temporal upscalers, like FSR2, typically replace the temporal AA part of the frame. So if we run the numbers in this slide, we can calculate that our upscaler needs to be less than 4.6 milliseconds less, and it needs to consume less bandwidth than 130 megabytes per frame. Because going above these values doesn't really make sense, and we might as well render at full resolution. And here is a breakdown of the stock FSR2 running on the G720 device. If we focus on the 540 to 1080 upscaling, we'll see that the total time spent in the upscaler is almost 6 milliseconds, and the total bandwidth it's around 235 megabytes. So we are 1.4 milliseconds and 103 megabytes of bandwidth more than our absolute minimum target, which is not great. So we need to start optimizing, and let's start from the top with the order of execution. The first pass is the compute luminance pyramid dispatch. Let's start with that. This is basically AMD's single pass downsampler that does reduction of exposure data to fill 2 MIP levels of the texture and optionally compute the final exposure. By looking at the Mali flying compiler, we can spot a few things. Shared memory is quite high. A note here, Mali doesn't have a dedicated fast-on-chip memory for group shared storage, so this will result on additional bandwidth and load store overhead. We can also spot register spilling. The register is using more the shader is using more registers than the hardware has available, and the extra are spilled into main memory, and this translates to bandwidth. By looking at streamline, bandwidth is quite high, and SPD shouldn't be taking 2 milliseconds or 3 milliseconds, really. So something must be really off. So apparently, the shader compiler was unrolling loops, resulting in massive register spilling. Turns out that SPD's quad reduction function was using wave intrinsics to emulate quad operations. This is probably a leftover because the GLSL path of SPD is using actual quad operations. So moving to quad intrinsics in HLSL gave the compiler the hints it needed to not actually unroll this case, and this led to all register spilling thus magically going away. SPD also supports a floating point 32 and a 16 floating point path. So with a few changes, we were able to enable the FP16 path and squeeze a few extra cycles, and at the same time reduce the size required for the group shared memory. And using our quality, image quality workflow verification, we didn't spot any quality regression, so yeah, we moved forward with these changes. These are the results. By getting rid of the spilling and moving to FP16, we managed to get a massive bandwidth and runtime reduction. For the 540 internal target, for example, the time went from 2.4 milliseconds to almost nothing. And bandwidth dropped a few orders of magnitude from 100 to 1.6 megabytes. So apparently, yeah, this was a low-hanging fruit. Next pass is the reconstruct previous depth. This is an auxiliary pass that generates dilated motion vectors and depth. It also does reconstruction of last frame's depth to be used later to build the dissolution mask. By looking at Mali flying compiler, we see high load store usage. This can probably be explained by the multiple UAV outputs. Streamline tells us that the duration of this dispatch is not too high, but bandwidth is a little bit on the high side. So for this pass, we will focus on bandwidth and the elimination of the load store instructions. This dispatch can be easily moved to fragment shading, and this will allow almost every render target to benefit from FBC. We only need to keep one texture in UAV because that requires atomic operations to get updated. A small parenthesis here, FBC is ARM's frame buffer compression, which is a technology that compresses render targets for improved bandwidth and runtime performance. So UAVs, also known as storage images in Vulkan, disable FBC. So writing textures from compute will not give you FBC's benefits. So in other words, if you set the storage bit in a Vulkan image, will flat out disable FBC. So by looking at the shader, we also got some additional ideas for improvements, but with a few quality sacrifices. Maybe we can do those at some point later under a special performance preset. Right, so by moving to fragment shading, and we almost have the load store instructions. The remaining that you see there are from the texture that is getting updated using atomics. For the 540 internal resolution, the workload duration went down 38%, and the bandwidth 34%. So, and higher gains for the higher resolutions. So yeah, not bad results overall. Next up is depth clip pass. This pass stores the YCOG encoded tone-mapped input color and builds a dilated reactive mask based on user input, disocclusion, and general motion. Looking at this, at the Mali-Flying compiler, we see a balanced pass overall, but maybe it's a little bit high on the bandwidth side. And also, we spot some high load store and texturing instructions. Similar treatment to the previous pass. We move everything to fragment shading to benefit from AFBC. We can also convert some parts of the shader to FP16, specifically the code related to sampling, color, data, and some logic around the computation of the reactive mask. So this pass uses RGBA 16-bit textures to store its output. The two chroma components go from -1 to 1, and the alpha channel holds the disocclusion factor, which is from 0 to 1. So yeah, maybe 16-bit is a little bit of an overkill for these ranges. And this felt like something worth optimizing, but we decided to leave it untouched until some later point, because it would result in probably some quality degradation. For this stage, we also micro-optimize some texture operations. There are a few places where the shader is sampling a texture 9 times using a 3x3 box kernel, and it's using texel fetch. For this one, we tried 2 texture gather operations to sample 7 texels, and for the remaining corners, we just used texel fetch. And this resulted into 4 texture operations instead of 9. And this is the final state of depth clip. The texture optimizations, along with some FP16 conversions and the move to FBC, decreased the duration by 27% for the 540p case. And but the biggest improvement was bandwidth by -40%. Log pass is cheap, so we didn't bother too much. We did some minor optimizations around texturing kernels, and that gave us some minor bandwidth improvements. And now the accumulate pass, which is actually the heart of FSR2. It does spatial upscaling, temporal reprojection. It consumes all the intermediate buffers of the previous passes and produces the final image. This was the most expensive pass on Mali in both duration and bandwidth, because 2.7 milliseconds is quite a lot for a pass. Mali-Flying compiler also showed quite a bit of register spilling, and also high usage on all hardware units, especially load store. High load store might be because of register spilling, but yeah, we'll see. The shader also is using some FP16, but probably not enough, so we will check that as well. Let's start with easy optimizations. It seems this pass can be moved to to fragment shading for FBC support. At this point, we'll also make an observation. The internal upscaled color texture uses RGBA 16-bit. RGB holds linear HDR values, and alpha stores a factor that goes from -1 to 1. Maybe this can be brought into a more efficient format, but since we don't want to regress on quality, we leave it as is for now, but we'll come to it later, so keep a mental note. Once again, we focused on the texture operations, and particularly those in the spatial upsampling and the one that is doing history projection. Both operations use a significant amount of samples, and everything is interpolated using custom interpolators. FSR2 uses 4x4 bicubic kernels with Langsos, but it also offers some alternatives. We experimented with Langsos approximation and a smaller 3x3 kernel. And according to our image quality framework, this didn't have any significant impact on quality. Furthermore, we also micro-optimized some texture axes using gather ops, similar to some previous passes. And overall, we went from 16 texel fetch operations to something like 8 texture operations in general. Next goal was to eliminate the register peeling, which was the biggest problem. For that, we tried to move as many instructions we could to FP16. We used the SMOS to visualize the ranges of various variables in the shader. And if some of these values vary from, let's say, -1 to 1, we could probably move them to FP16, since 16-bit precision is mostly fine for such a range. But we also need to be careful not to introduce casting instructions from FP32 to FP16, and the opposite. This conversion operations will appear as CVT instructions in the Malio-Flying compiler. CVT is the converting unit. We also moved the code around the spatial upsampling and history projection to FP16, since these functions operate on color data, and 16-bit is often good enough for those, especially on mobile. For the final thing was micro-optimizations in the shader logic, basically moving things around until Malio-Flying compiler stops reporting spilling. Yeah, usual stuff. And here's the final state of the accumulate pass. The spilling fortunately went away. FP16 usage increased to 44%, and arithmetic, texture, and especially load store instructions went down. This pulse now almost runs at double the speed, and it consumes 61% less bandwidth. So yeah, good results overall. ARCAS is the optional sharpening pass of FSR2. Looking at the Malio-Flying compiler, again, we see high load store. And by looking at streamline, the duration and bandwidth are also a bit on the high side, for a sharpening pass at least. But I will not bore you with details. For ARCAS, we moved to fragment shading and enabled the FP16 arithmetic path of the shader. Since this is an optional pass, we didn't bother too much optimizing it. But overall, we see a 33% reduction in the pass's duration and a 56% reduction in bandwidth. And this is a video that compares FSR2 against ASR. It's difficult to spot any differences in a video, but hopefully we'll be able to share the slide deck and you can view the video yourself in your big screen. And this is how we ended up with what we call a quality preset, which is roughly 100% match to FSR2 in terms of quality. The duration varies from 2 to 2.7 milliseconds, which is below our budget. And bandwidth varies from 75 to around 100 megabytes, which is a little bit on the high side, at least for mobile content. We have quite a few ideas to take these numbers further down, but this would result in minor quality degradation. Fortunately for us, though, the high pixel density of smartphone screens means that we can cut really some corners on that. This is another way to visualize the duration and bandwidth improvements of our optimizations for Mali hardware. Left gray box is duration, right is bandwidth, left bar is FSR2, and the right bar is ASR quality. Now let's see the compromises we made to improve performance even further. Yeah, I mentioned that before. The devices we're targeting allow us some headroom for some cheating, and we can exchange some quality for additional performance. For that, we decided to introduce what we call shader quality presets. These presets are orthogonal to the upscaling ratios, and I'm mentioning that because some popular upscalers use the terms quality, balanced, and performance for the upscaling ratios. In our case, it's not that. Quality is the authentic FSR2 experience, but optimized for mobile. It's for high-end content without any quality compromises. Balance tries to find the sweet spot between quality and duration and bandwidth. This is for less demanding content that is less sensitive, to some minor quality loss. And finally, we have the performance, which is more aggressive, which has more aggressive quality to performance trade-offs. For balance per set, we try to keep the quality up, but decrease the bandwidth even further. The accumulate pass is still the most expensive one, and that was our first target. The plan is to cut some heuristics that don't have much impact. You may also remember the temporal reactive factor and the comments we made about it. We can encode this differently by separating the factor in its own 8-bit render target and move the history color to a more bandwidth efficient format. Lastly, we took a look at some texturing kernels, and we tried to cut some corners there as well. In terms of image quality, the balance percent is quite close to quality one. We managed to get between 12 to 21% reduction in the overall passage duration. And, but the biggest win was in bandwidth from 16 to 24% reduction. And here is a similar view to one we had previous, and this one also has FSR2, ASR quality, and ASR balanced. For the performance preset, we were willing to make additional quality sacrifices, but without breaking our test content. All these sacrifices, of course, cannot make the performance preset worse than special upscalers in terms of quality, at least for the 2x upscaling. This time we'll focus on the passes before accumulation. And in order to achieve our goals, we looked at a few things. The most important ones were the history projection was simplified to a Catmull ROM 5-tab kernel. And we did some work in the prepared input color render target in depth clip. We now store tone mapped RGB directly without YCOG encoding. And this RT is now in RGB 111110 format. These are the results. Some small improvements in bandwidth, around 50%, 15%. And these are FSR2 and all ASR presets side by side. Now let's see some actual content. We'll use our internal demo called Mori. Mori is built in Unreal Engine 5. This is a simple frame breakdown. We couldn't fit the whole renderer into a single slide, so we kept a few key passes. On the left side, there is a traditional different renderer with direct lighting and lumen for indirect. This runs in the internal resolution. ASR follows in the middle and does upscaling and AA. And on the right side, we have post-processing and UI rendering. These passes typically happen in full resolution. And this is a video. The frame rate, in some cases, jumps from 20 to 39 FPS. And here are a few more detailed numbers taken from a power-instrumented G720 device. Duration improved from 1.5x to 2x, depending on the preset. And since we have a power-instrumented device, we could also look at power data. And we can spot the FPS per watt also improved from 1.4 to 1.8x. Now some closing thoughts. But first, let's talk delivery. The experience kit is a combination of multiple components with a goal of helping the ecosystem to access the technology. We will release the Arm-ASR experience kit as open source in early 2025 under the MIT license, and the package will contain the source code of ASR, of course, tutorials and samples, and also plugins for the major game engines. We have a beta version for the Unreal 5 plugin, and we'll soon have one for Unity as well. Now, when it comes to future work, at the moment we are improving ASR based on feedback, especially the performance preset. We are also evaluating a transition to the new FFX API of FSR3. Adopting the new API will help to simplify integration even further and generally improve the developer experience. And finally, we will keep talking to developers, working on the adoption and support of ASR. And now we reach the end. Feel free to scan the code for updates. And of course, big thanks to AMD for creating FSR and releasing it for free. Thank you. Now I think we have some time for questions.
Hi, thanks for the talk. It was really interesting to see all the performance optimization stuff. So I noticed there was lots of use of fragment shaders to take advantage of AFBC, with lots of rendering stuff moving more and more into compute pipelines. Is there any thought of ability to leverage AFBC from within, from output from compute kernels?
So that's in our minds always. But yeah, at least the current generation of GPUs cannot do that. But I don't know, maybe in the future. Yeah.
Hello, thank you for the talk. I was wondering about your thought process for starting with FSR2. Did you try anything different before it, or did you always assume that FSR2 would be your starting point?
No, I think that was our first try, and we wanted to check the numbers if we were satisfied. We didn't necessarily need to develop something new. So yeah, we were happy with what we had, and we were lucky with the optimizations. So we didn't look into something custom that needs extensive testing, unlike FSR2, which is quite battle tested.
Any other questions? Okay, no? Then thank you very much,
Thank you.
Panos.